Loopring, a decentralized token exchange protocol. Daniel Wong, Daniel at loopring.org, J at loopring.org, Alex Wong, Alex at loopring.org, Matthew Finestone, Matt.Finestone at gmail.com, https://loopring.org, April 6, 2018. Abstract. Loopring is an open protocol for building decentralized exchanges. Loopring operates as a public set of smart contracts responsible for trade and settlement, with an off-chain group of actors aggregating and communicating orders. The protocol is free, extensible, and serves as a standardized building block for decentralized applications, DApps, that incorporate exchange functionality. Its interoperable standards facilitate trustless, anonymous trading. An important improvement over current decentralized exchange protocols is the ability for orders to be mixed and matched with other, dissimilar orders, obviating the constraints of two-token trading pairs and drastically improving liquidity. Loopring also employs a unique and robust solution to prevent front-running, the unfair attempt to submit transactions into a block quicker than the original solution provider. Loopring is blockchain agnostic and deployable on any blockchain with smart contract functionality. At the time of writing, it's operable on Ethereum 1, 2, and TOM 3, with Neo 4. Under construction. 1. Introduction. With the proliferation of blockchain-based assets, the need to exchange these assets amongst counterparties has significantly increased, as thousands of new tokens are introduced, including the tokenization of traditional assets. This need is magnified, whether exchanging tokens for speculative trading motivations, or converting to access networks via their native utility tokens. The ability to exchange one crypto asset for another is foundational for the larger ecosystem. Indeed, there is a potential energy in assets. 5. And realizing this energy, unlocking capital, requires not only asserting ownership, which blockchains have immutably allowed for, but the ability to freely transfer and transform these assets. As such, the trustless exchange of tokens, value, is a compelling use case for blockchain technology. Until now, however, crypto enthusiasts have largely settled for trading tokens on traditional centralized exchanges. The Loopring protocol is needed because, just as Bitcoin 6 dutifully emphasized that, in regards to peer-to-peer electronic cash, the main benefits are lost if a trusted third party is still required to prevent double spending. So too are the main benefits of decentralized assets lost if they must pass through trusted, gated, centralized exchanges. Trading decentralized tokens on centralized exchanges doesn't make sense from a philosophical perspective, as it fails to uphold the virtues these decentralized projects espouse. There are also numerous practical risks and limitations in using centralized exchanges, which are described below. Decentralized exchanges, DEXs, 7, 8, 9, have sought to address these issues, and in many cases have succeeded in alleviating security risks by using blockchains for disintermediation. However, as DEX capability becomes crucial infrastructure for the new economy, there is substantial room for performance improvement. Loopring aims to provide modular tools for said infrastructure with its DApp-agnostic open protocol to current exchange landscape. 2.1 Inadequacies of centralized exchanges. The three primary risks of centralized exchanges are 1. Lack of security, 2. Lack of transparency, and 3. Lack of liquidity. Lack of security arises from users typically surrendering control of their private keys, funds, to one centralized entity. This exposes users to the possibility that centralized exchanges fall prey to malicious hackers. The security and hacking risks facing all centralized exchanges are well known. 10, 11, yet are often accepted as table stakes for token trading. Centralized exchanges continue to be honeypots for hackers to attack, as their servers have custody over millions of dollars of user funds. Exchange developers can also make honest, accidental errors with user funds. Simply, users are not in control of their own tokens when deposited at a centralized exchange. Lack of transparency exposes users to the risk of dishonest exchanges acting unfairly. The distinction here is by the exchange operator's malicious intentions, as users are not truly trading their own assets on centralized exchanges, but rather, an IOU. When tokens are sent to the exchange's wallet, the exchange takes custody and offers an IOU in its place. All trades are then effectively between users' IOUs. To withdraw, users redeem their IOU with the exchange and receive their tokens to their external wallet address. Throughout this process there is a lack of transparency, and the exchange can shut down. freeze your account, go bankrupt, etc. It is also possible that they use user assets for other purposes while in custody, such as lending them out to third parties. Lack of transparency can cost users without a total loss of funds, such as in higher trading fees, delays at peak demand, regulatory risk, and orders being front-ran. Lack of liquidity. From the point of view of exchange operators, fragmented liquidity inhibits entry by new exchanges because of two winner-takes-all scenarios. First, the exchange with the greatest number of trading pairs wins, because users find it desirable to conduct all their trades on one exchange. Second, the exchange with the largest order book wins, because of favorable bid-ask spreads for each trading pair. This discourages competition from newcomers because it is difficult for them to build up initial liquidity. As a result, many exchanges command a high market share despite user complaints and even major hacking incidents. It's worth noting that as centralized exchanges win market share, they become an ever larger hacking target. From the point of view of users, fragmented liquidity significantly reduces user experience. In a centralized exchange, users are only able to trade within the exchange's own liquidity pools, against its own order book, and between its supported token pairs. To trade token A for token B, users must go to an exchange that supports both tokens or register at different exchanges, disclosing personal information. Users often need to execute preliminary or intermediate trades, typically against BTC or ETH, paying bid-ask spreads in the process. Finally, the order books may not be deep enough to complete the trade without material slippage. Even if the exchange purports to process large volumes, there is no guarantee that this volume and liquidity is not fake. 12. The result is disconnected silos of liquidity and a fragmented ecosystem that resembles the legacy financial system, with significant trading volume centralized on few exchanges. The global liquidity promises of blockchains hold no merit within centralized exchanges. 2.2 Inadequacies of decentralized exchanges. Decentralized exchanges differ from centralized exchanges in part because users maintain control of their private keys, assets by performing trades directly on the underlying blockchain. By leveraging the trustless technology of cryptocurrencies themselves, they successfully mitigate many of the above-mentioned risks surrounding security. However, problems persist in regards to performance and structural limitations. Liquidity often remains an issue as users must search for counterparties across disparate liquidity pools and standards. Fragmented liquidity effects are present if DEXs or dApps at large don't employ consistent standards to interoperate, and if orders are not shared propagated across a wide network. The liquidity of limit order books, and, specifically, their resiliency, how fast-filled limit orders are regenerated, can significantly affect optimal trading strategies. 13. The absence of such standards has resulted not only in reduced liquidity, but also exposure to an array of potentially insecure proprietary smart contracts. Furthermore, since trades are performed on-chain, DEXs inherit the limitations of the underlying blockchain, namely, scalability, delays in execution, mining, and costly modifications to orders. Thus, blockchain order books do not scale particularly well, as executing code on the blockchain incurs a cost, gas, making multiple order cancellation cadences prohibitively expensive. Finally, because blockchain order books are public, the transaction to place an order is visible by miners as it awaits being mined into the next block and placed into an order book. This delay exposes the user to the risk of being front-run and having the price or execution move against him. 2.3 Hybrid solutions. For the above reasons, purely blockchain-based exchanges have limitations that make them uncompetitive with centralized exchanges. There is a trade-off between on-chain inherent trustlessness and centralized exchange speed and order flexibility. Protocols such as Loopring and 0x. 14. Extend a solution of on-chain settlement with off-chain order management. These solutions revolve around open smart contracts, but navigate scalability limitations by performing several functions off-chain and giving nodes flexibility and fulfilling critical roles for the network. However, drawbacks remain for the hybrid model as well. 15. The Loopring protocol proposes meaningful differences in our approach to a hybrid solution throughout this paper. 3. Loopring protocol. Loopring is not a DEX, but a modular protocol for building DEXs on multiple blockchains. We disassemble the component parts of a traditional exchange and offer a set of public smart contracts and decentralized actors in its place. The roles in the network include wallets, relays, liquidity sharing consortium blockchains, order book browsers, ring miners, and asset tokenization services. Before defining each, we should first understand Loopring orders. 3.1 Ordering. Loopring orders are expressed in what we call a unidirectional order model, UDOM. 16. UDOM expresses orders as token exchange requests, amount to sell by, instead of bids and asks. Since every order is just an exchange rate between two tokens, a powerful feature of the protocol is the mixing and matching of multiple orders in circular trade. By using up to 16 orders instead of a single trading pair, there is a dramatic increase in liquidity and potential for price improvement. Order number 2 owner, Y amounts, 9B amount, 12C. Order number 1 owner, X amounts, 10,000 A amount, 2B. Order number 3 owner, Z amounts, 100C amount, 160A 7,898 A 8B 98C. Figure 1. An order ring of 3 orders. The above figure shows an order ring of 3 orders. Each order's token to sell, tokens, is another order's token to buy, token. It creates a loop that allows each order to exchange their desired tokens without requiring an opposing order for its pair. Traditional order pair trades can, of course, still be executed, in what is essentially a special case of an order ring. Definition 3.1. Order ring. Let C0, C1, CN1 be n different tokens, O01, OII1, on 10 BN orders. Those orders can form a order ring for trading, O01, OII1, on 10, where n is the length of the order ring, and I1 plus 1 mod n an order. Ring is valid when all component transactions can be executed at an exchange rate equal to or better than the original rate specified implicitly by the user. To verify order ring validity, Loopring protocol smart contracts must receive order rings from ring miners where the product of the original exchange rates of all orders is equal to or greater than 1. Let's assume Alice and Bob want to trade their token A and B. Alice has 15 token A and she wants 4 token B for them. Bob has 10 token B and he wants 30 token A for them. Who is buying and who is selling? This depends only on the asset we fixed to give price quotations. If token A is the reference, then Alice is buying token B for the price of 15.4 equals 3.75 A, while Bob is selling 10 token B for the price of 30.10 equals 3.00 A. In the case of fixing token B as reference, we say that Alice is selling 15 token A for the price of 4.15 equals 0.2666667 B and Bob is buying 10 token A for the price of 10.30 equals 0.33333334 B. Hence, who's the buyer or seller is arbitrary. In the first situation, Alice is willing to pay a higher price, 3.75 A, than the price Bob is selling his tokens for, 3.00 A. While in the second situation Bob is willing to pay a higher price, 0.33333334 B, than the price Alice is selling her tokens for, 0.2666667 B. It is clear that a trade is possible whenever the buyer is willing to pay an equal or higher price than the seller's price. 15.430.10 equals 10.34.15 equals 15.4, 10.30 equals 1.25 is greater than 1. Thus, for a set of n orders to be able to be filled, fully or partially, we need to know if the product of each one of the exchange rates as by orders results in a number greater or equal to 1. If so, all the n orders can be either partially or totally filled. 17. If we introduce a third counterparty, Charlie, such that Alice wants to give X1 token A and receive Y1 token B, Bob wants to give X2 token B and receive Y2 token C, and Charlie wants to give X3 token C and receive Y3 token A, the necessary tokens are present, and the trade is possible if X1, X2, X3, Y1, Y2, Y3 is greater than or equal to 1. 2. See Section 7.1 for more details about Loopring's orders for ecosystem participants. The following ecosystem participants jointly provide all functionalities a centralized exchange has to offer. Wallets, a common wallet service or interface that gives users access to their tokens and a way to send orders to the Loopring network. Wallets will be incentivized to produce orders by sharing fees with ring miners. See Section 8. With the belief that the future of trading will take place within the safety of individual users' wallets, connecting these liquidity pools through our protocol is paramount. Consortium Liquidity Sharing Blockchain Relay Mesh, a relay mesh network for order and liquidity sharing. When nodes run Loopring relay software, they are able to join an existing network and share liquidity with other relays over a consortium blockchain. The consortium blockchain we are building as a first implementation has near real-time order sharing, 1-2-second blocks, and trims old history to allow for faster download by new nodes. Notably, relays need not join this consortium. They can act alone and not share liquidity with others, or they can start and manage their own liquidity sharing network. 3. Relays. Ring miners. Relays are nodes that receive orders from wallets or the relay mesh, maintain public order books and trade history, and optionally broadcast orders to other relays via any arbitrary off-chain medium, and/or relay mesh nodes. Ring mining is a feature, not a requirement, of relays. It is computationally heavy and is done completely off-chain. We call relays with the ring mining feature turned on ring miners, who produce order rings by stitching together disparate orders. Relays are free in 1. How they choose to communicate with one another, 2. How they build their order books, and 3. How they mine order rings. Mining algorithms. Loopring Protocol Smart Contracts, LPSC, a set of public and free smart contracts that checks order rings received from ring miners, trustlessly settles and transfers tokens on behalf of users, incentivizes ring miners and wallets with fees, and emits events. Relays order browsers listen to these events to keep their order books and trade history up to date. See Appendix A for details. Asset tokenization services, ATS, a bridge between assets that cannot be directly traded on Loopring. They are centralized services run by trustworthy companies or organizations. Users deposit assets, real, fiat or tokens from other chains, and get tokens issued, which can be redeemed for the deposit in the future. Loopring is not a cross-chain exchange protocol, until a suitable solution exists, but ATS enable trading of ERC20 tokens, 18, with physical assets as well as assets on other blockchains. 5. Exchange Process 1. Protocol Authorization. In Figure 2, user Y who wants to exchange tokens authorizes the LPSC to handle amounts of token B the user wants to sell. This does not lock the user's tokens, who remains free to move them while the order is processed. 2. Order creation. The current rate and order book for token B versus token C are provided by relays or other agents hooked up to the network, such as order book browsers. User Y places an order, limit order, specifying amounts and amount and other parameters through any integrated wallet interface. An amount of LRX can be added to the order as a fee for ring miners. Higher LRX fee means a better chance to be processed earlier by ring miners. The order's hash is signed with user Y's private key. 3. Order broadcast. The wallet sends the order and its signature to one or more relays. Relays update their public order book. The protocol doesn't require order books to be built in a certain way, such as first come first serve. Instead, relays have the power to make their own design decisions in building their order books. 4. Liquidity sharing. Relays broadcast the order to other relays through any arbitrary communication medium. Once again, there is flexibility how whether nodes interact. To facilitate a certain level of network connectivity, there is a built-in liquidity sharing relay mesh using a consortium blockchain. As mentioned in the prior section, this relay mesh is optimized for speed and inclusivity. User X, user Y, user Z, relay N, order 1 owner, X amounts, 10,000 A amount, 2B order 2 owner, Y amounts, 9B amount, 12C order 3 owner, Z amounts, 100C amount, 160A order 1 owner, X amounts, 10,000 A amount, 2B order 2 owner, Y amounts, 9B amount, 12C order 3 owner, Z amounts, 100C amount, 160A blockchain accounts account E accounts account M account and LPSC share liquidity ring mining submit ring 7898 A8B 98C fee 213456 settlement. Figure 2. Loopring exchange process. 5. Ring mining. Order matching. Ring miners try to fill the order fully or partially at a given exchange rate or better by matching it with multiple other orders. Ring mining is the main reason why the protocol is able to provide high liquidity over any pair. If the executed rate is better than what user Y specified, margin is shared amongst all orders in the order ring. As a reward, the ring miner chooses between claiming part of the margin split, and giving back the LRX to the user, or simply keeping the LRX fee. 6. Verification and settlement. The order ring is received by LPSC. It makes multiple checks to verify the ring miner supply data and determines if the order ring can be settled fully or partially, depending on the fill rate of orders in ring and tokens in users' wallets. If all checks are successful, the contract atomically transfers the tokens to users and pays the ring miner and wallet fees at the same time. If user-wise balance as determined by the LPSC is insufficient, it will be considered scaled down. A scaled-down order will automatically scale up to its original size if sufficient funds are deposited to its address, unlike a cancellation, which is a one-way manual operation and cannot be reversed. 6. Operational flexibility. It's important to note that Loopring's open standard allows participants significant flexibility in how they operate. Actors are free to implement novel business models and provide value for users, earning LRX fees on volume or other metrics in the process, if they so choose. The ecosystem is modular and meant to support participation from a multitude of applications. 6.1 Order book relays can design their order books in any number of ways to display and match users' orders. A first implementation of our own order book follows an OTC model, where limit orders are positioned based on price alone. Timestamps of orders, in other words, have no bearing on the order book. However, a relay is free to design their order book in such a way as to emulate a typical centralized exchange's matching engine, where orders are ranked by price, while respecting timestamps as well. If a relay was inclined to offer this type of order book, they can integrate with a wallet, and have those wallet orders sent solely to the single relay, who would then be able to match orders based on time. Any such configuration is possible, whereas other DEX protocols at times require relays to have resources, initial token balances to place taker orders. Loopring relays need only find matchable orders to consummate a trade, and can do so without initial tokens. 6.2 Liquidity sharing relays are free to design how they share liquidity, orders, with each other. Our consortium blockchain is but one solution to accomplish this, and the ecosystem is free to network and communicate as they wish. Besides joining a consortium blockchain, they can build and manage their own, creating rules and incentives as they see fit. Relays can also work alone, as seen in the time-sensitive wallet implementation. Of course, there are clear advantages in communicating with other relays in pursuit of network effects. However, different business models could merit peculiar sharing designs and split fees in any number of ways. 7 Protocol Specification 7.1 Anatomy of an order. An order is a pack of data that describes the intent of the user's trade. A Loopring order is defined using the Unidirectional Order Model, or UDOM, as follows: message order, address protocol, address owner, address tokens, address token, 256 amounts, 256 amount, unit 256 LRC fee, unit 256 valid since, second since epoch, unit 256 valid until, second since epoch, und 8 margin split percentage, 100, pool by no more than amount, 256 wallet ID, dual authoring address, address auth adder, V, R, S are parts of the signature und 8V, bytes 32R, bytes 32S, dual authoring private key, not used for calculating orders hash, thus it is not signed string auth key, 256 nonce. To ensure the origin of the order, it is signed against the hash of its parameters, excluding auth adder, with the user's private key. The auth adder parameter is used for signing order rings that this order is part of, which prevents front-running. Please reference section 9.1 for more details. The signature is represented by the V, R, and S fields, and is sent alongside the order parameters over the network. This guarantees the order stays immutable during its whole lifetime. Even though the order never changes, the protocol can still compute its current state based on the balance of its address along with other variables. UDOM doesn't include a price, which must be a floating point number by nature, but instead uses the term rate or R, which is expressed as amount. The rate is not a floating point number but an expression that will only be evaluated with other unsigned integers on demand. To keep all intermediate results as unsigned integers and increase calculation accuracy. 7. 1 by amounts. When a minor ring matches orders, it's possible that a better rate will be executable, allowing users to get 5 more token than the amount they specified. However, if by no more than amount is set to true, the protocol ensures users receive no more than amount of token. Thus, UDOM's by no more token parameter determines when an order is considered completely filled. By no more token applies a cap on either amounts or amount, and allows users to express more granular trade intentions than traditional buy-sell orders. For example, with amounts equals 10 and amount equals 2, the rate R equals 10/2 equals 5. Thus the user is willing to sell 5 tokens for each token. The ring minor matches and finds the user a rate of 4, allowing the user to receive 2.5 token instead of 2. However, If the user only wants 2 token and set the buy no more than amount flag to true, the LPSC performs the transaction at a rate of 4 and the user sells 4 tokens for each token, effectively saving 2 tokens. Keep in mind this does not take into account mining fees. See Section 8.1. Indeed, if we use order, amounts, tokens, amount, token, buy no more than token, to represent an order in a simplified form, then for ETH/USD markets on a traditional exchange, traditional buy-sell modeling can express the first and the third order below, but not the other two. 1. Sell 10 ETH at price of 300 USD ETH. This order can expressed as order 10 ETH 3000 USD. False 2. Sell ETH at price of 300 USD ETH to get 3000 US dollars. This order can expressed as order 10 ETH 3000 USD. True 3. Buy 10 ETH at price of 300 USD ETH. This order can expressed as order 3000 USD 10 ETH. True 4. Spend 3000 US dollars to buy as many ETH as possible at price of 300 USD ETH. This order can expressed as order 3000 USD 10 ETH. False 7.2 Ring verification. The Loopring smart contracts do not perform exchange rate or amount calculations, but must receive and verify what the ring miners supply for these values. These calculations are done by ring miners for 2 main reasons. 1. The programming language for smart contracts, such as Solidity 19 on Ethereum, does not have support for floating point math, especially POW X 1/n, calculating the nth root of a floating point number. And 2. It is desirable for the computation to be made off-chain to reduce blockchain computation and cost. 7. 2. 1 sub. Ring checking. This step prevents arbitrageurs from unfairly realizing all the margin in an order ring by implementing new orders within it. Essentially, once a valid order ring is found by a ring miner, it could be tempting to add other orders to the order ring to fully absorb the user's margin. Rate discounts, as illustrated by Figure 3 below, carefully calculated x1, y1, x2 and y2 will make the product of all orders rate be exactly 1, so there will be no rate discount. Order 2 owner, y amounts, 9b amount, 12c order 1 owner, x amounts, 10,000 a amount, 2b order 3 owner, z amounts, 100c amount, 160a order 4 owner, m amounts, x1a amount, y1b order 5 owner, address sum amounts, x2c amount, y2a. Figure 3. An order ring with subring. This is zero risk, zero value add to the network, and is considered unfair conduct by the ring miner. To prevent this, Loopring requires that a valid loop cannot contain any subrings. To check this, the LPSC ensures a token cannot be in a buy or sell position twice. In the above diagram, we can see that token A is a sell token twice and a buy token twice, which would be disallowed. 7. 2. Fill rate checking. The exchange rate calculations in the order ring are made by ring miners for reasons stated above. It is the LPSC that must verify they're correct. First, it verifies that the buy rate the ring miner can execute for each order is equal to or less than the original buy rate set by the user. This ensures the user gets at least the exchange rate they asked for or better on the transaction. Once the exchange rates are confirmed, the LPSC ensures that each order in the order ring shares the same rate discount. For instance, if the discounted rate is Greek letter gamma, then the price for each order will be R01, 1 Greek letter gamma, R12, 1 Greek letter gamma, R20, 1 Greek letter gamma, and satisfy R01, 1 Greek letter gamma, R12, 1 Greek letter gamma, R20, 1 Greek letter gamma, equals 1, 3. Hence, Greek letter gamma equals 113 R01, R12, R20, 4. If the transaction crosses n orders, the discount is Greek letter gamma equals 11 NQQ and 1I equals 0 RI. 5. Where RI is the order turnover rate of ith order. Obviously, only when the discount rate is Greek letter gamma 0, can these orders 6 be filled, and the ith order I's actual exchange rate is RI equals RI, 1 Greek letter gamma, RI. Recall our prior example where Alice has 15 token A and wants 4 token B for them. Bob has 10 token B and wants 30 token A for them. If token A is the reference, then Alice is buying token B for 15.4 equals 3.75 A, while Bob is selling token B for 30.10 equals 3.00 A. To calculate the discount, 150 120 equals 1.25, thus 1.25 equals 0.8 equals 1 Greek letter gamma, 2. Thus the exchange rate that renders the trade equitable for both parties is 0.8, 3.75, 3.3541 token A per token B. Bob gives 4 token B and receives 13.4164 token A, more than the 12 he was expecting for those 4 tokens. Alice receives 4 token B as intended but gives only 13.4164 token A in exchange, less than the 15 she was willing to give for those 4 tokens. Note: a portion of this margin will go towards paying fees to incentivize miners and wallets. See Section 8.1, 7, 2, 3. Field tracking and cancellation. A user can partially or fully cancel an order by sending a special transaction to the LPSC, containing the details about the order and the amounts to cancel. The LPSC takes that into account, stores the amounts to cancel, and emits an order canceled event to the network. The LPSC keeps track of filled and canceled amounts by storing their values using the order's hash as an identifier. This data is publicly accessible and order canceled, order filled events are emitted when it changes. Tracking these values is critical for the LPSC during the order ring settlement step. LPSC also supports canceling all orders for any trading pair with the orders canceled event and canceling all orders for an address with the all orders canceled event. 7. 2. 4. Order scaling. Orders are scaled according to the history of filled and canceled amounts and the current balance of the sender's accounts. The process finds the order with the smallest amount to be filled according to the above characteristics and uses it as a reference for scaling all transactions in the order ring. Finding the lowest value order can help to figure out the fill volume for each order. For instance, if the ith order is the lowest value order, then the number of tokens sold from each order S and number of tokens purchased B from each order can be calculated as SI equals C, BI equals SIRI, SI1 equals BI, BI1 equals SI1RI1, SI2 equals BI1, BI2 equals SI2RI2, where C is the balance left after orders are partially filled. During implementation we can safely assume any order in the order ring to have the lowest value, then iterate through the order ring at most twice to calculate each order's fill volume. Example: if the smallest amount to be filled compared to the original order is 5%, all the transactions in the order ring are scaled down to 5%. Once the transactions are completed, the order that was considered to have the smallest amount remaining to be filled should be completely filled. 7.3 Ring settlement. If the order ring fulfills all the previous checks, the order ring can be closed, and transactions can be made. This means that all AN orders form a closed order ring, connected as in Figure 4, 0103020405 on Figure 4. Ring settlement. To make the transactions, the LPSC uses a token transfer delegate smart contract. The introduction of such a delegate makes upgrading the protocol smart contract easier, as all orders only need to authorize this delegate instead of different versions of the protocol. For each order in the order ring, a payment of tokens is made to the next or the previous order depending on the implementation. Then the ring miner's fee is paid depending on the fee model chosen by the ring miner. Finally, once all the transactions are made, a ring mined event is emitted. 7. 3. 1. Emitted events. The protocol emits events that allow relays, order browsers, and other actors to receive order book updates as efficiently as possible. The emitted events are: order cancelled, a specific order has been cancelled; orders cancelled, all orders of a trading pair from an owning address have been cancelled; all orders cancelled, all orders of all trading pairs from an owning address have been cancelled. Ring mined, an order ring has been settled successfully. This event contains data related to each in-ring token transfer. 7.8 LRX token. LRX is our generalized token notation. LRC is the Loopring token on Ethereum, LRQ on TOM, and LRN on Neo, etc. Other LRX types will be introduced in the future as Loopring is deployed on other public blockchains. 8.1 Fee model. When a user creates an order, they specify an amount of LRX to be paid to the ring miner as a fee, in conjunction with a percentage of the margin split percentage, made on the order that the ring miner can claim. This is called a margin split. The decision of which one to choose, fee or margin split, is left to the ring miner. A representation of the margin split: total by amount order, original by amount, additional by amount, margin split order, actual by amount margin. Figure 5. A 60% margin split. If the margin on the order ring is too small, a ring miner will choose the LRX fee. If, on the contrary, the margin is substantial enough for the resulting margin split to be worth much more than the LRX fee, a ring miner will choose the margin split. There is another proviso, however, when the ring miner chooses the margin split, they must pay the user, order creator, a fee, which is equal to the LRX the user would have paid to the ring miner as a fee. This increases the threshold of where the ring miner will choose the margin split to twice the LRX fee of the order, increasing the propensity of the LRX fee choice. This allows ring miners to receive a constant income on low-margin order rings for the trade-off of receiving less income on higher-margin orderings. Our fee model is based on the expectation that as the market grows and matures, there will be fewer high-margin order rings, thus necessitating fixed LRX fees as incentive. We end up with the following graph. YXF2FF expected mining income figure 6. Loopring's fee model where F is the LRX fee, X is the margin split, Y is the mining income, Y equals max, F, XF, as indicated by the solid line. If the LRX fee for the order is 0, the equation is Y equals max, 0, X 0. That simplifies to Y equals X as indicated by the gray line. The consequences are, 1. If the margin split is 0, ring miners will choose the flat LRX fee and are still incentivized to. If the LRX fee is 0, the gray line results and the income is based on a general linear model. 3. When the margin split income is greater than 2x, LRX fee, ring miners choose the margin split and pay LRX to the user. It should be noted that if the LRX fee is non-zero, no matter which option the ring miner chooses, there will always be a transfer of LRX between the ring miner and the order sender. Either the ring miner earns the LRX fee, or pays the LRX fee back to the sender to take the margin split. Ring miners will share a certain percentage of fees with wallets. When a user places an order through a wallet and gets filled, the wallet is rewarded with a portion of the fees or margin split. Although this is modular, and unique business models or implementations are possible, our inclination is for wallets to receive approximately 20% minus 25% of earned fees. Wallets represent a primary target for Loopring protocol integration as they have the user base, but little or no source of income. 8.2 Decentralized governance at its root. The Loopring protocol is a social protocol in the sense that it relies on coordination amongst members to operate effectively towards a goal. This is not dissimilar to cryptoeconomic protocols at large, and indeed, its usefulness is largely protected by the same mechanisms of coordination problems. 20. Grim trigger equilibrium and bounded rationality. To this end, LRX tokens are not only used to pay fees, but also to align the financial incentives of the various network participants. Such alignment is necessary for broad adoption of any protocol, but is particularly acute for exchange protocols, given that success rests largely on improving liquidity in a robust decentralized ecosystem. LRX tokens will be used to effectuate protocol updates through decentralized governance. Smart contract updates will, in part, be governed by token holders to ensure continuity and safety, and to attenuate the risks of siphoned liquidity through incompatibility. Given that smart contracts cannot be altered once deployed, there is a risk that dApps or end users continue to interact with deprecated versions and preclude themselves from updated contracts. Upgradability is crucial to the protocol's success as it must adapt to market demands and the underlying blockchain's 8 decentralized governance by LRX stakeholders will allow for protocol smart contract updates without disrupting dApps or end users, or relying too heavily on smart contract abstraction. LRX tokens have a fixed supply, and in the case of LRC, certain percentages are frozen from the Loopring Foundation and allocated to community-purposed funds. 21. However, LRX token owners are not the only stakeholders to consider in steering the protocol's direction. Relays, ring miners, wallets, developers, and others are an integral part of the ecosystem and their voice must be heard. In fact, given that these agents need not hold any LRX to perform their respective roles, since traditional makers-takers and market makers are non-existent, initial token reserves are not mandatory. We must allow alternative methods for their interests to be respected. Furthermore, simple token-based voting, both on-chain and off, is an imperfect solve for disagreement, as low voter turnout and token ownership concentration pose risks. Thus, the goal is to implement a governance model that is built in layers, and rests on a shared knowledge that some set of decision-making processes is the norm. This can be facilitated by coordination institutions that offer signals from a diverse set of participants, and, perhaps, from pre-established protocol focal points. As this comes to fruition, The Loopring Foundation will inevitably evolve from protocol developers into protocol stewards. 9 Fraud and Attack Protections. 9.1 Front Running Prevention in Decentralized Exchanges. Front running is when someone tries to copy another node's trade solution and have it mined before the original transaction that is in the pending transaction pool, mempool. This can be achieved by specifying a higher transaction fee, gas price, the major scheme of front running and loopring, and any protocol for order matching, or order filch. When a front runner steals one or more orders from a pending order ring settlement transaction, and, specific to loopring, when a front runner steals the entire order ring from a pending transaction, when a submit ring transaction is not confirmed and is still in the pending transaction pool, anyone can easily spot such a transaction and replace miner address with their own address, the filcher address. Then they can resign the payload with filcher address to replace the order ring signature. The filcher can set a higher gas price and submit a new transaction, hoping block miners will pick his new transaction into the next block instead of the original submit ring transaction. Previous solutions to this problem had important downsides, requiring more transactions and thus costing ring miners more gas, and taking at least twice the blocks to settle an order ring. Our new solution, dual authoring, 22, involves the mechanism of setting up 2 levels of authorization for orders, one for settlement, and one for ring mining. Dual authoring process. 1. For each order, the wallet software will generate a random public key-private key pair, and put the key pair into the order's JSON snippet. An alternative is to use the address derived from the public key instead of the public key itself to reduce byte size. We use auth_adder to represent such an address, and auth_key to represent auth_adder's matching private key. 2. Compute the order's hash with all fields in the order except R, V, S, and auth_key, and sign the hash using the owner's private key, not auth_key. 3. The wallet will send the order together with the auth_key to relays for ring mining. Ring miners will verify that auth_key and auth_adder are correctly paired and the order's signature is valid with respect to owner address. 4. When an order ring is identified, the ring miner will use each order's auth_key to sign the ring's hash, miner address, and all the mining parameters. If an order ring contains n orders, there will be n signatures by the n auth_keys. We call these signatures the auth signatures. The ring miner may also need to sign the ring's hash together with all mining parameters using miner address's private key. 5. The ring miner calls the submit ring function with all the parameters, as well as all the extra auth signatures. Notice that auth_keys are not part of the on-chain transaction and thus remain unknown to parties other than the ring miner itself. 6. The Loopring protocol will now verify each auth signature against the corresponding auth_adder of each order, and reject the order ring if any auth signature is missing or invalid. The result is that now, the order's signature by the private key of the owner address guarantees the order cannot be modified, including the auth_adder. The ring miner's signature by the private key of the miner address, if supplied, guarantees nobody can use his identity to mine an order ring. The auth signatures guarantees the entire order ring cannot be modified, including miner address, and no orders can be stolen. Dual authoring prevents ring filch and order filch while still ensuring the settlement of order rings can be done in one single transaction. In addition, dual authoring opens doors for relays to share orders in 2 ways, non-matchable sharing and matchable sharing. By default, 9 Loopring operates an OTC model and only supports limitless orders, meaning that orders' timestamps are ignored. This implies that front-running a trade has no impact on the actual price of that trade, but does impact whether it gets executed or not. 10 Other attacks. 10.1 Sybil or DOS attack. Malicious users, acting as themselves or forged identities, could send a large amount of small orders to attack Loopring nodes. However, since we allow nodes to reject orders based on their own criteria, which they may hide or reveal, most of these orders will be rejected for not yielding satisfying profit when matched. By empowering relays to dictate how they manage orders, we do not see a massive tiny order attack as a threat. 10.2 Insufficient balance. Malicious users could sign in spread orders whose order value is non-zero but whose address actually has 0 balance. Nodes could monitor and notice that some orders' actual balance is 0, update these order states accordingly and then discard them. Nodes must spend time to update the status of an order, but can also choose to minimize the effort by, for example, blacklisting addresses and dropping related orders. 11 Summary. The Loopring protocol sets out to be a foundational layer for decentralized exchange. In so doing, it has profound repercussions in how people exchange assets and value money as an intermediate commodity. facilitates or replaces barter exchange and solves the double coincidence of wants problem. 23. Whereby two counterparties must desire each other's distinct good or service. Similarly, Loopring protocol aims to dispense of our dependencies on coincidence of wants in trading pairs, by using ring matching to more easily consummate trades. This is meaningful for how society and markets exchange tokens, traditional assets, and beyond. Indeed, just as decentralized cryptocurrencies pose threat to a nation's control over money, a combinatorial protocol that can match traders, consumers, producers, at scale, is a theoretical threat to the concept of money itself. Protocol benefits include off-chain order management and on-chain settlement means no sacrifice in performance for security, greater liquidity due to ring, mining and order sharing. Dual authoring solves the pernicious problem of front-running faced by all DEXs and their users today. Free, public smart contracts enable any DApp to build or interact with the protocol. Standardization among operators allows for network effects and an improved end-user experience. Network maintained with flexibility in running order books and communicating. Reduced barriers to entry means lower costs for nodes joining the network and end users. Anonymous trading directly from user wallets. 12 acknowledgements. We would like to express our gratitude to our mentors, advisors and to the many people in the community that have been so welcoming and generous with their knowledge. In particular, we would like to thank Shuo Bai, from China Ledger, Professor Habin Khan, Alex Chang, Hongfa Ida, Yin Xiao, Ziachuan Wu, Jin Wang, Wei Yu, Nian Duan, Jun Xiao, Jiang Jin, Jiangsu Xiong, Yipan Guo, Dai He Li, Kelvin Long, Huaxia, Jun Ma, and Encephalopath for reviewing and providing feedback on this project. References: 1. Vitalik Buterin, Ethereum, a next-generation smart contract and decentralized application platform, 2013, URL http://Ethereum.org Ethereum HTML, 2017. 2. Gavin Wood, Ethereum, a secure decentralized generalized transaction ledger, Ethereum project Yellow Paper, 151, 2014. 3. Patrick Dye, Neil Mahi, Jordan Earls, and Alex Norda, smart contract value transfer protocols on a distributed mobile application platform, URL, https://qtum.org uploads files CF6D 69348 K50DD 985B 60425 CCF 282 F3 PDF, 2017. 4. Victor Aterolon, a distributed ledger for gamification of pro bono time, 2018. 5. Hernando de Soto, The Mystery of Capital, Basic Books, 2006. Satoshi Nakamoto, Bitcoin, a peer-to-peer electronic cash system, 2008. 7. Fabian Shu and Daniel Larimer, BitShares 2.0, Financial Smart Contract Platform, 2015. 8. Bancor Protocol, URL https://bancor.network, 2017. 9. Yaron Velner Loyalu, Kyber Network, a trustless decentralized exchange and payment service, https://kr.kyber.network/assets/Kyber Network Whitepaper PDF, accessed, March 5, 2018. 10. Fortune, how to steal $500 million in cryptocurrency, http://fortune.com/2018/01/31/coincheck accessed, March 30, 2018. 11. Robert McMillan, The Inside Story of Mt. Gox, Bitcoin's $460 million disaster, 2014. 12. Sylvain Rebis, Chasing Fake Volume, a Crypto Plague, https://medium.com/@SylvainartPlayribes/Chasing Fake Volume, a Crypto Plague A103C1E0B5E, accessed, March 10, 2018. 13. Risela Aliardi and Ramazan Jene, Hedging Through a Limit Order Book with Varying Liquidity, 2014. 14. Will Warren and Amir Bandili 0x, an open protocol for decentralized exchange on the Ethereum blockchain, 2017. 15. Ido Bentov and Lawrence Breitenbach, The Cost of Decentralization, http://hackingdistributed.com/August 13, 2017. Cost of Decent, accessed, March 5, 2018. 16. Daniel Wong, Co-Imports Implementation of UTM https://jithub.com/duang77/backcore/glub/master coinex backend src main scal.com co-import coinex market manager scalab accessed March 5, 2018. 17. Supersymmetry. Remarks on Loopring https://docs.loopring.org PDF Supersymmetry Loopring Remark PDF accessed March 5, 2018. 18. Fabian Vogelschuler, ERC, Token Standard, URL https://jithub.com Ethereum EAPS Issues 20, 2015. 19. Chris Dannon, Introducing Ethereum and Solidity, Springer, 2017. 20. Vitalik Buterin, Notes on Blockchain Governance https://vitalik.ca General December 17, 2017 Voting HTML, accessed March 5, 2018. 21. Loopring Foundation, LRC Token Documents https://docs.loopring.org English Token, accessed March 5, 2018. 22. Daniel Wong, Dual Authoring Loopring Solution to Front Running, URL https://medium.com/loopring protocol/dual-authoring-looprings-solution-to-front running-D0FC9C348EF1, 2018. 23. Nick Szabo, Menger on Money, Right and Wrong http://unenumerated.blogspot.ca/2006/06 Menger on Money Right and Wrong HTML, accessed March 5, 2018. Appendices Appendix A Loopring implemented on EVM Loopring Protocol IMPA Loopring Protocol Name Registry Token Registry Transferable Multisig Token Transfer Delegate, Validates order rings, transfers tokens for settlement, emits events, registers wallets and relays, defines interfaces and events, registers ERC20/ERC223 tokens, enables multi-signature, transfers tokens on behalf of users ownership Figure 7, Smart Contracts 11 Appendix B Deployment B, 1 Ethereum The following smart contracts have been deployed on Ethereum Mainnet, LRC, 0s F6087C694 F40C8202821 EDF 525D 3,782,458,639 F, Token Registry, 0s A21C1 F2AE7 F721AE77 B1204 A4 F0811C642,638.9, Token Transfer Delegate, 0x7B126 AB811 F278 F288 BF1D62 D47,334,351.20 D1D, Name Registry, 0xD181C1808 E3 F010 F0 F0 AABC6 B1 BCE 2025 DB7 BB7, Loopring Protocol Impl. 0x0B48 B747,436 F10C 846,696 E889 E66425 E05 CD 740 FB, 2 TUM The following smart contracts have been deployed on TUM Mainnet, LRQ, 2 Eb2 A66 AFD4 E465 FB068 B71 F30 FB1 B93 E18788D, Token Registry, C89A A34,360,258,917 DAF 3,655 F8 BEC 5,550,923,509 B3, Token Transfer Delegate, 60 B3 FA7 F461,664 E4 DAF 621 A36 AC 2722 CC 680 F10, Name Registry, E26 A27 D92,181,069 B25 BC 7283 E03722 F6 7678 BB, Loopring Protocol Impl. 5180 BB 56 B 696 D 16635 Abdate DC 235 E0 E 432 ABF 25 D.